Okay, you guys, we're going to start this chapter 14, which is Inference about the model, which basically is looking back at our linear regression work and making some inferences or, tests and intervals concerning scatterplots or linear regression. So let me just start with a little scenario. Just a second. Okay, so let's imagine a scatter plot. The thing that this really starts to discuss is the fact that when we do scatter plots, when we had paired data, the sample, the data that we were looking at was really a sample of a bigger population, which lets you start to consider intervals and significance tests because you're looking at one sample. So what would repeated samples look like? So let's just imagine some two variables that had a huge population of members, and we just have tons and tons and tons of dots. So let's say we've got some bit of positive correlation, but we just have tons and tons and tons. So let's say this is all American ninth graders, and this is your length at birth, and this is your height in ninth grade. It could be the first day of your freshman year, something like that. So you can imagine, there's, we call it length because babies aren't standing up, but you've got just a huge, cloud of dots for all of these millions and millions and millions of freshmen. And some would be, it wouldn't be this steady of a pattern. We might have some people who are really short but grew up really tall, so there might be some dots that don't follow the pattern, but you get the idea. So let's say you take a sample of a bunch of freshmen, and the thing about it is one sample might be this freshman, and this freshman, and this freshman, and this freshman, and this freshman. We'd probably want more than 5, but one sample would give us a linear regression equation like that. So what we are doing when we take this sample is we are saying that this red line, which is the closest line we could get to all of our red dots, is hopefully a pretty good estimator of, overall the whole population. Maybe it is, maybe it's not. Let's try some yellow dots. What if your sample just happened to be this person and this person and this person and this person and this person? Those would create a completely different linear regression equation, and you could do this all day, every time creating a different regression equation. You could get these people right here by chance, but to do that would be a less likely sample because you got more people on the outskirts of the sample where people are more rare. But the point is, repeated sampling out of a big population would make a different regression equation every time, and that's what inference is about. Sometimes when all of the intervals of tests we've done so far, there's always a chance, a small chance, that you get something that's away from the crowd. It's just always a possibility. That's why nothing we say is ever certain. So, what this is based on is we're going to be coming up with 3 estimators. Let's say U sub y equals alpha plus beta y. This is our true regression. This basically is the unknown. Alpha and beta are our unknown slope and intercept. That we are going to work on estimating our inference techniques. And those are basically what would happen if you were somehow able to get a scatter plot of every single freshman in the United States and make a regression line with every single person, so that it was the whole sample, the whole population, not just a sample. An interesting picture that's pretty helpful is, let's just imagine that we looked at all, let's see, length at birth. Let's see everybody who was 20 inches long at birth. If you were to look at all 20-inch babies, then their heights in 9th grade should follow a normal distribution, if whatever the average 20-inch baby turns out to be. So let's say they end up being, I don't know what a 20-inch baby would be in freshman year. Let's say they ended up being 5'7", with a certain standard deviation of maybe a couple inches. So my point is that 20-inch babies have one distribution, 21-inch babies have another distribution, and every single length baby has its own distribution. There's kind of a 3D picture. It's a little bit tough to draw, but let's say that this is length at birth. There's a picture of this in your book that might be better to look at. What we're trying to do is come up with a picture for where this true regression line is. So at each particular birth, I'm going to take this normal curve that I just drew, and I'm going to kind of try to draw it in 3D over here. So maybe that's 18-inch babies and 20-inch babies and 22-inch babies and so on. So in 3D, I get my little normal curves for each particular height. For example, 18, 20, 23. And this could be for any height, any length baby there is. But each one corresponds to its own little normal curve in 3D. That's kind of hard to see. Basically, what we're doing here is this unknown slope and intercept and unknown regression line is going right through the bottom middle of each one of those. This right here is that unknown true regression line. Maybe another way to picture it would be to go to our original, and let's say this is 20 inches. Then if you go up from there, you should get a normal distribution where whatever the average height is for 20-inch babies, you got a bunch of dots in there, and then you get more widespread as you move away from there. So you've got a little, it's like you're looking down on top of the little normal curve. It's kind of hard to draw if you're looking straight down on it, but if you have a little bit of angle to it, you're looking down on a bunch of little normal curves that all follow the pattern, that all follow the pattern upward. So it's very hard to visualize, but hopefully you get the idea. We can talk about it more when I'm talking to you in person. So let's talk about, this is kind of the basis, and visually it's hard to see. Let's talk about what you're going to have to do. Okay, so there are three issues here. Issue number one is the slope of the line. Okay, our sample is going to give us y hat equals a plus bx. Okay, this is just regular linear regression like you've known how to do for months. Okay, A is an unbiased estimator of alpha, which means that repeated samples, if you were to keep taking sample after sample, the A values that you get should have a distribution that's the same center as alpha, which means that if my sample has an intercept of 4, then I don't have any reason to suspect that my population doesn't have an intercept of 4. Okay, B is an unbiased estimator of beta. So those are the two parts of the equation. The only thing left to discuss is, what about the standard deviation? These little curves all are going to have the same standard deviation. We need to come up with an estimator of those. We have an estimator for alpha, that's A. We have an estimator for beta, that's B. We need an estimator for our standard deviation of each curve. So let's talk about that. What we're going to use is the standard error about the line. Just as we've used in the past, S is going to be our estimator of lowercase sigma for standard deviation. So let's just cut to the chase. Here's the equation for it. 1 over n minus 2. It turns out you have n minus 2 degrees of freedom with these. I'll talk more about that later as well. Times the sum of the residuals squared. Or, another way to say it, 1 over n minus 2. Residual is a term from a while ago, which is the difference between the actual and the predicted, y minus y hat, where y hat is the predicted. And this is going to estimate the standard deviation. All right, so make sure you have those formulas down. And if you're working this standard error out by hand, what you'll want to do to make it easier is to use your lists in your calculator to find your residuals. And then if you do one variable stats, you can get the sum of all of them squared, and then you can divide by n minus 2, and then you can square root it. We'll talk about that later. Okay, so quickly, the last thing I want to show you is confidence intervals. So what we're going to be finding here is I've got a sample slope, and this is going to be, I should be more specific, confidence interval for slope. My sample gave me one slope, and what I want is a confidence interval around that slope that tells me how sure I am of the population's actual slope. So this can be done in the calculator, but here's the old-fashioned way. B is the slope from the sample that I actually took, times T star, and you should remember this from our T distribution, times the standard error for B, where standard error for B equals S, which we just talked about, over the square root of the sum of x minus x bar. So you take each x value, subtract the mean, square those values, add them up, square root it, the whole deal. After maybe once or twice, you're not going to do this by hand, probably ever again. This is going to be mostly done in the calculator, but get this formula down just in case. You never know when a question is going to come up where you have to use a part of the formula. And that's that. So, little deep for a video set of notes, but the basic point is your population scatterplot would be millions of dots depending on the population. When we do a sample, we're getting one of many potential lines. What we're trying to come up with is patterns that would happen if you were to repeat your sample many, many times again. So we're just kind of applying the things we've been doing for the last 4 or 5 chapters onto our old work with scatterplots. So that's that. Make sure you have these formulas, and we will see what kind of problems come up with that in class. All right? Young out.